Perfect. So our title is Risks from Learned Optimization in Advanced Machine Learning Systems. And here is a bit about our speaker, Evan. Evan Hubinger is an AI Safety Research Fellow at the Machine Intelligence Research Institute. Before joining MIRI, Evan was an AI Safety Research Intern at OpenAI. His current work is aimed at solving inner alignment for iterated amplification. Evan was an author on risks from learned optimization in advanced machine learning systems, was previously a MIRI intern, designed the functional programming language Coconut, and has done software engineering work at Google, Yelp, and Ripple. Finally, Evan has a Bachelor of Science in Mathematics and Computer Science from Harvey Mudd College. So now I will hand over to Evan to begin his talk.
Wonderful. All right, yeah, so like Jake was saying, I'm going to be talking about risk and learned optimization. This talk is based on a paper of which I am a co-author, and so a lot of the stuff that I'm going to be talking about is all, credit should also go to the other co-authors that are at the bottom of the page. Okay, so just first a little bit about me. I was, Jake was just saying, but I currently am a researcher at MIRI. I used to work at OpenAI. I did a bunch of other stuff at other places before that also. And then also maybe just a little bit about this talk. So this talk is has a long storied history now at this point. So this is a talk that I gave originally at Chai as part of their sort of seminar series, and then also at OpenAI and as a Google Tech Talk on this sort of paper that I mentioned that I worked on for a long time with a bunch of other people, many of whom were at Oxford at the time, as well as Scott, who was at MIRI, really trying to sort of dig into what I saw at the time as sort of one of the really biggest sort of underappreciated things in AI safety. So we're going to talk a lot about that as we go. So, all right, what are we talking about? So I think it's really sort of a good idea to start from a perspective of what is machine learning again, and how does it work? Because I think a lot of times when we think about AI safety and we think about, what is it that we're concerned about, I think that a lot of times we can sort of get lost in the clouds and forget what's really going on. So what does machine learning do? So fundamentally, machine learning says, well, we're going to take in some parameter space, we're going to take in some loss function, we're going to take in some data, and then we're going to take our parameters, sample from our parameter space randomly, and then iteratively sample some data, and then take steps around that parameter space based on the gradient of the loss function over that data. So this is actually a very complex procedure. And so when we're trying to sort of figure out how to understand this sort of procedure, that is just sampling things from our model space and then just sort of walking around according to the gradient, we have abstractions that we can use to try to on a higher level try to figure out what's going on. And a very common abstraction that I see a lot of times that people make when they sort of try to understand this process is what I call the does the right thing abstraction. So what is the does the right thing abstraction? Well, the does the right thing abstraction says that, well, when we do this process, the model's parameters end up being selected to minimize the loss function because we're stepping around the parameter space according to the gradient of the loss over the sort of data. So therefore, we can think of the model, because it was selected to minimize the loss function, as really trying to minimize that loss. Even potentially over the full distribution, not just over the individual data points that it was trained on. We sort of take the model and we deploy in a new environment where we expect it to keep trying to minimize that same loss that it was selected under. And you can see why this is called the does the right thing abstraction, because this is what we want our machine learning models to do. But when we sort of sample, when we get a model and we select it according to some loss function, we're trying to get a model which is actually trying to minimize that loss. But all abstractions are leaky, and this abstraction, in particular, is leaky. There's the law of leaky abstractions is that all non-trivial abstractions to some degree are leaky. There are some ways in which your abstraction, despite the fact that because it is an abstraction, because it is not actually describing the actual complex phenomenon of gradient descent, there are going to be cases where the abstraction doesn't hold. A particular case where we sort of are going to be investigating a place where this abstraction doesn't hold is the situation of optimizers. So what is an optimizer? So I'm going to say that a system is an optimizer if it is internally searching through some space, looking for those elements that score high according to some internally represented objective. So what do I mean by some space? So, it could be policies, plans, strategies, just outputs, whatever. So some examples, just to sort of make this a little bit more clear. So gradient descent is an optimizer because gradient descent is searching through the space of possible models, and it is trying to look for those models which perform well on the loss function. Minimax would be an optimizer because it is doing a search over possible actions, trying to get those which perform well on some objective function. Humans are optimizers because we do search over possible plans, strategies, trying to find those that we like the best. Things that are not optimizers. So a classic example here is a bottle cap. So why might it seem like a bottle cap is an optimizer? Well, you can make an argument that a bottle cap is an optimizer at keeping water in a bottle because it's really good at it. Whatever you do, whatever things you do to the bottle, it's always going to be the case that the bottle cap is very well made for keeping water in a bottle. What actually happened though isn't that the bottle cap itself is an optimizer, but that humans are good optimizers, and we optimize the bottle cap to keep the water in a bottle. And that distinction is going to be very important. And also, a randomly initialized neural net is almost certainly not an optimizer. It's just some random linear algebra calculation that isn't going to be doing some coherent optimization. That's not necessarily true after we train the model. So what happens if we train a neural network or some other model? And as a result of that training, we do end up with an optimizer. In that situation, we're going to call it a MESA optimizer. So I have this diagram here. I'm going to try to explain what's going on. So we're going to say that a model that is itself implementing some optimization output. You train your neural network, and that neural network internally is doing some search. In that case, we're going to call that neural network, the whole network, a MESA optimizer. And we're going to say that it has a MESA objective. Whatever it is trying to optimize for is its MESA objective. In that situation, it's the model that you actually care about in terms of its input-output behavior, because it's the model that's going to be taking actions in the world. But that model, it was optimized by gradient descent, which we'll call the base optimizer. And it has some base objective, which is the loss function that it was trained over. Okay, so we have base optimizer, which is gradient descent. We have the model, the sort of what we'll call the learned model, which is the model produced by gradient descent. And if the learned model is an optimizer, then we'll call it a MESA optimizer with some MESA objective. Okay, and the term MESA here comes from Greek. MESA is the opposite of meta. So you sort of might be familiar with meta optimization, meta learning, which is common as a sort of technique in machine learning, where we sort of create another optimizer on top. And so we're sort of concerned in some sense about emergent meta learning. What happens when your gradient descent process ends up being a meta learning process, sort of even though you didn't intend? Because it turns out that your model just actually is an optimizer. Okay, so this is why we call it a MESA optimizer. All right, so some misunderstandings here that are worth trying to clear up. So MESA optimizer does not mean subsystem. So by MESA optimizer, I'm not referring to some component of the model, but rather the entire learned model. Right? And MESA optimizer is just a learned model that is doing search. Okay. So I was just talking about how this relates to meta learning, right? So MESA optimization is spontaneous emergent meta learning, right? So this is from Pedro et al., meta learning of sequential strategies. So from DeepMind, so what do they say? They say that the downside of spontaneous meta learning is that we cannot easily control what will be meta learned. In particular, spontaneous meta learning can lead to undesirable emergent properties, which is considered an open research problem at AIC. And this is the problem we're really going to be tackling in depth. It's this problem of what happens when you start doing meta learning, but you didn't intend to do meta learning, where your gradient descent process ends up selecting not just over some grab bag of heuristics, but over some really coherent optimizer as the sort of model that it's training. Okay, so in this situation, I said previously this is a situation where the does the right thing abstraction is leaky. And so that's sort of what we're going to dig into. So what happens when you have a MESA optimizer to the does the right thing abstraction? Does it still hold? How likely is it to hold? What happens to it? So if we take the does the right thing abstraction and we translate it into the domain of MESA optimizers, we get that the does the right thing abstraction of MESA optimizers is the model's MESA objective should directly be to minimize the loss. It should care about, it should be selecting for, it should be optimizing for making the loss as low as possible, because that's what it was trained under, right? And so if it does the right thing, that's what it should do. Okay, but what happens with an abstraction links? It's just an abstraction. This doesn't actually describe the sort of process of machine learning, and so it can be leaky. So we're going to take the sort of overall alignment problem, which you might be familiar with, which is, just the problem of producing AIs that are, doing the right thing, that are aligned with their sort of programmer's intentions. And we're going to split it into two components in the situation where there's sort of leaks in this abstraction. So the outer alignment problem is the problem of aligning the base objective, which is to say the loss function of your gradient descent process, the reward function of your reinforcement learning process, or whatever, with the programmer's intentions. We want that, the sort of thing that the gradient descent process is selecting for, to be something you actually want. And then we also have the inner alignment problem. And the inner alignment problem is a problem which, in the case of a MESA optimizer, it is aligning the MESA objective of that learned model with the base objective, the loss function. Okay, so in the inner alignment problem is sort of trying to tackle this problem of, well, what if, that abstraction is leaky and we end up with a model that is trying to optimize something that is different than the loss function? How do we prevent that? Okay, so what does an inner alignment failure look like? So you might have seen stories of what outer alignment failures look like paperclip maximizers or whatever. I want to tell a story of what it might look like for inner alignment to fail. So when inner alignment fails, we'll say that your capabilities generalize, but your objective does not. So what do I mean by that? So I'm going to give an example. So let's say we train our model in the sort of following training environment. We have this small sort of brown maze and it has this green arrow at the end. And our loss function is we sort of select the model, we sort of reward the model for finishing the maze. Okay, and now we want to deploy the model to this new environment. But there's a couple of things that are different about this new environment. It's a different color, it's larger, and importantly, we have the green arrow at a different location than the end of the maze. And now we want to ask the question, how does our model generalize to this new environment? And there's a couple of different things that can happen in this new environment. So one thing that can happen is that in this new environment, the model just can't generalize. It fails to get to the end. It fails to sort of just be able to navigate the maze at all. It just can't do anything sort of meaningful or coherent in the new environment. And this would be a situation where we'd say its capabilities didn't generalize. It didn't learn a general purpose enough maze solving algorithm, a sort of optimization algorithm, that was able to sort of generalize to the new maze. Okay, but there's other things that can happen as well. It could be that its capabilities do generalize. It learns a general purpose maze solving algorithm, and it uses that, algorithm in the deployment environment to get to the end of the maze. That would be a situation where its capabilities generalized and its objective generalized. It sort of did the right thing on the new environment. It used its sort of powerful maze solving optimization algorithm that it learned on the training environment for the right purpose on the deployment environment, get to the end of the maze. But there's a third thing that can happen here as well, which is, well, what happens if its capabilities generalize? It learned a really good sort of general purpose maze solving algorithm, but its objective doesn't generalize. Rather than trying to use that maze solving algorithm to get to the end of the maze, it uses it to go to the green arrow. So why would this happen? Well, on the training environment, these two sort of strategies look identical because we put the green arrow at the end. And so there's sort of an unidentifiability here where the model sort of, we can't tell just on the training environment whether it's going to generalize in one way or generalize in another way. And so we're just relying on it being the case in this environment that the objective is going to generalize properly, that it's going to learn that what we really cared about was the end of the maze rather than the green arrow. But in fact, we have no guarantee of that. And if we end up in a situation where the model is, its capabilities generalized, it learns a sort of really powerful general purpose optimization algorithm that's able to generalize to sort of more powerful, more complex environments, but its objective doesn't generalize, then what that means is that we're in a situation where we have created a model that is really powerful, that has sort of, a powerful general purpose optimization algorithm, but that it's directed at the wrong place, that it's pointing that optimization algorithm at a sort of objective that we never intended, that we never wrote down, that we never tried to train on. And that's scary. And I think it's basically scary for the same reasons that sort of any AI, alignment problem is scary. It's scary because now we have a powerful AI system out there that is doing something that we don't want it to do. Okay. So I'm going to put some terms to these things. So we're going to say that a model is robustly aligned if it is aligned over the whole data distribution. That is to say, a maze optimizer with an objective of finishing the maze in the previous example. And we're going to say that a maze optimizer is pseudo-aligned if it's only aligned over the training data. If it looks aligned over all of the data points we can check, but when it sort of is deployed to some new environment, when it sort of is forced to generalize, it might not be aligned. So this is a maze optimizer with an objective of trying to find the green arrow. Okay, so now there are two problems that are sort of suggested by this, which are the sort of two problems we're going to be tackling in this talk. So the first problem is unintended optimization, which is when your model is an optimizer, when you end up with a maze optimizer, sort of why would that happen even when you don't want it to be? What would cause the sort of model that is produced by your gradient descent process to be an optimizer even when you're not trying to produce an optimizer? And then the interlining problem, which is when in fact your learned model is a maze optimizer, what will its objective be, and how do we ensure that that objective is aligned with the base objective? All right, so we're going to start with the unintended optimization problem. So we want to know what are the conditions for maze optimization? What sorts of machine learning systems are more or less likely to find maze optimizers? Okay. So I think the first point that I'll make, which I think is a really sort of pretty general point, is that, well, search generalizes really well. So what do I mean by that? Well, search algorithms have the ability to handle really diverse environments because they get to sort of take in this sort of, they don't have to sort of have their behavior hard-coded in advance, right? So if you think about comparing a sort of, heuristic-based algorithm to a search-based algorithm and sort of putting them in sort of some complex environment, in some sense, the sort of heuristic-based algorithm doesn't, it has to sort of, its heuristics have to already be selected to perform well in that environment. But a search-based algorithm can sort of look at the environment, be like, okay, I can deduce some features of the environment and then figure out what is going to be the most sort of effective strategy for me in this specific, environment that I currently find myself in, figure out that strategy, then implement it. And so in this sense, search gets to be really general because it has the ability to sort of do this very, very general sort of, figure out what's correct in the environment. If you think about something like, why is it the case that, search does so well on, something like, if we look at sort of current algorithms, something like mu0, why is it that something like mu0 is so effective at solving all of these different broad, diverse environments? It's really good at solving both, Go and also Atari and all of these different things. It's like, well, it's because it has access to this really powerful Monte Carlo tree search algorithm. It has access to this really powerful search algorithm, which is able to take some sort of, basic details of the environment and figure out what's the sort of most powerful thing to do in that situation, sort of in general. So search is really powerful, has the ability to generalize really well. And so in any situation where we're hoping that our model is going to generalize, where we're trying to sort of, get generalization across a really broad, diverse set of environments, we should expect search, I think. Okay. But furthermore, search is a form of compression. So what do I mean by that? Well, if we think about the sort of heuristic-based algorithm versus the search-based algorithm, well, the search-based algorithm just sort of is the heuristic-based algorithm, but with the ability to figure out what the heuristics are. Rather than having the sort of, what should you do in this specific environment hard-coded, it looks at the environment, tries to reason about and do search for what is the best strategy in this environment, and then executes that. And that's a compression process. It's a process of taking this sort of really complex policy and compressing it down into a very simple algorithm that is just, do some forward pass on like what is going to be the thing that like in fact causes, your objective to be most satisfied. So, okay. Given that search is compression, why might we expect, compressed policies to be selected for by our machine learning processes? And I think there's a couple of strong reasons for this. So the first thing is, well, there's just some good evidence that deep learning tends to be biased towards simple functions. It tends to be biased towards sort of models that are in fact simpler. And we can sort of formalize this. There are some formalizations that actually sort of use Kolmogorov complexity and demonstrate that there's like a relationship there between inductive biases and sort of computational complexity. There's also just sort of more general things. There's sort of one paper that I have up here that's looking at this sort of relationship between the sort of parameter function map, which is the relationship between sort of how you sort of select your neural network's parameters and what the actual sort of function is that it ends up implementing that is sort of heavily biased towards simplicity. Okay, there's also evidence that the sort of way we do random initialization is heavily biased towards simplicity. So there's a lot of evidence there. Another thing which also I think is relevant here, which you may or may not be familiar with, is the double descent phenomenon. So if you've ever sort of taken a machine learning course, you've probably seen the sort of classical risk curve where we have sort of training risk, where as we sort of increase the complexity of our model, our sort of training error goes down, but our sort of test error goes down and then goes back up again because we sort of underfit and then we overfit. Okay, but double descent says this isn't the end of the story. Actually, if you keep increasing complexity past what's called the interpolation threshold, which is the point where you reach sort of a training risk of 0, then the test risk actually starts going back down again and can in fact do better than it ever did in the sort of classical regime. So why is this the case? Well, so this is a phenomenon now that's sort of been studied a bunch. It was originally introduced by Belkin et al., which is the sort of diagram that I have, but it's also been demonstrated to sort of in fact exist empirically for a lot of various neural network systems, including image networks and language models. And what's going on here, at least according to Belkin et al., is that, well, when we're at the interpolation threshold, we don't give our model the ability to sort of make use of its simplicity prior. That when we sort of have this machine learning process, we're trying to select for, not just models which do well on loss function, but also models which are simple. And in the sort of, once we get to 0 training error, there's sort of only one possible model that sort of has, 0 training error that it can find at that point. And so it just is forced to select that one. But once you keep increasing complexity, there's a bunch of possible models, all of which have 0 training error, and the sort of training process will naturally select the simplest one. And by naturally selecting the simplest one, we actually get better generalization and ability to sort of avoid overfitting by relying on the sort of really powerful simplicity bias in our network, in our sort of training process. Okay, so there's lots of reasons why we might think that deep learning is biased towards simplicity, and that simplicity leads to Mace optimization. Okay, additionally, sort of another thing here is human modeling. So humans often act as optimizers, and so if you're in an environment where you're sort of you're incentivizing your models to do reasoning about humans, then that's likely to sort of already require them to they're already at least going to have the machinery of optimization, because they have to be able to have that machinery of optimization to predict what humans are doing. And so it's only a very simple step from there to be able to use that optimization machinery themselves. And in fact, this is what humans do. When we try to sort of model other humans, we reuse our own optimization machinery to do it. Okay, so sort of in summary, we have things that are going to incentivize Mace optimization, which are sort of really big models, large model sort of capacity, sort of implicit or explicit simplicity bias. And then another thing is statefulness, which is, well, if the model has the ability to store state over time, then it has the ability to sort of do more complex optimization calculations. Okay, things which might disincentivize Mace optimization. So if you have hard-coded optimization, like if you have something like MCTS explicitly in your model, then it has less of a reason to sort of have emergent optimization. We might have time complexity bias. Search might take more time than other sort of forms of things that you could do, and so sort of like the heuristic-based model is sort of faster, maybe potentially, even if it's sort of more complex. And then task restriction. If you just aren't doing really complex environments, then maybe that's a way to disincentivize Mace optimization. Okay, so when I look at these things, they're on the left and the right, it seems to me like as sort of AI has progressed, we have moved in a particular direction. We have moved towards larger and larger models, which have more ability to represent optimization. We've moved towards more simplicity bias. This is a weird one, but remember, double descent suggests that more complex models have a larger simplicity bias. That as we train our models for longer, the simplicity bias becomes more prominent. And this also shows up in other cases of the literature here. So I think we've moved towards more simplicity bias. We moved towards more statefulness, things like LSTMs, transformers. Transformers do have states. It's a little bit weird though. The state is the previous output of the transformer. Also, disincentivizing Mace optimization. The things that have sort of, these are things I think we've moved away from. So hard-code optimization, there are sort of models like Mu0 that are making use of this, but I think in large parts we've been moving towards more and more things being sort of end-to-end learned. Even Mu0 is sort of more end-to-end than something like AlphaZero. Sort of implicit explicit time bias, I think as we make our networks longer, the bias towards sort of very short computations is sort of going away, and we've moved towards more general environments. So it certainly seems to me like we are moving in a direction that is sort of likely to eventually lead us to Mace optimization, if we're not already there. Okay. So given that we're going to get Mace optimizers, we have to answer the question of how do we align them. And for the interalignment problem, we're concerned with the question of how do we align them just with the loss function. It's not even how do we produce Mace optimizers that are good, but just how do we produce Mace optimizers that are in fact sort of compatible with the does the right thing abstraction, that are like trying to do the thing that we wanted to get them to do. All right, so I'm going to talk about a couple different types of pseudo alignment, ways in which you can have a Mace optimizer that is, in fact doing the wrong thing. So, but it looks like it's doing the right thing on the training distribution. So we'll start with the most basic case, which is proxy pseudo alignment. So what is proxy pseudo alignment? Well, so the basic idea is that instead of trying to optimize for the actual loss function, which is we'll call O base, it's instead trying to optimize for some proxy, which is correlated with that sort of O base on the training environment, which is O mesa. So what does this correlation structure look like? Well, if we have a sort of causal graph, then O mesa and O besa have to have some sort of causal ancestor, such that this causal ancestor X, sort of when it increases, both O base and O mesa increase as well. And if that's the case, then if I'm a sort of optimizer for O mesa, then I will try to increase X to cause O mesa to go up, which will, as a side effect, result in O base going up. Okay, so this is, the basic structure of, the sort of what you might expect pseudo alignments to look like. But there are other possible ways, not just sort of proxy alignment. So suboptimality pseudo alignment is another possibility here. With suboptimality pseudo alignment, rather than the sort of objective being the thing that's causing pseudo alignment, it could be some deficiency or limitation in the model's optimization process. For example, once it starts thinking for longer, it'll realize that actually it shouldn't be doing what it's currently doing, and it'll stop looking aligned. Okay, so there's other possible ways, but we're primarily going to focus on proxy pseudo alignment. Okay, so that's what pseudo alignment looks like. Why would pseudo alignment actually be incentivized? So I sort of mentioned earlier in the sort of green arrow case, the sort of idea of unidentifiability, that, well, if you have a really diverse environment with tons and tons of different possible proxies that your model can sort of latch onto, with a really sort of dense causal structure of all of these sort of different things that are interacting, there's going to be a lot of instances of like various different things that are correlated to your desired objective, where there's some causal ancestor of both that thing and the actual objective you want. And in the sort of maze example, it was a very simple example. But it was constructed so as for there to exist some sort of simple proxy, which was, well, get to the green arrow. And on the training environment, getting to the green arrow and going to end of the maze were unidentifiable. Unidentifiable because there's no way to distinguish on the training environment between the model which does one and a model which does the other. Okay. And just a priori, as we move to more and more complex environments, we should expect there to be lots and lots of additional indistinguishable objectives. Things where, well, our environment is so complex, our causal structure is so complex, and our training data set is, very finite, such that there's going to be, lots of various different things that we're probably going to miss. Okay. But I think the problem is even worse than that. So, if the problem were just, well, we just need to make it so that everything is at least potentially identifiable on the training data set, maybe we could solve this problem just by increasing the training data set. But I think there are problems that are sort of even sort of worse than this. So, well, let me give you an example. So one way in which it could be the case that you could learn a proxy objective, even when it's actually performs worse on the loss function than the true objective, is if the proxy objective has some other benefit. One possible benefit that the proxy objective could have is it could be significantly faster and easier to compute than the sort of true desired loss function. So what does that mean? Well, you can have here's an example. One thing which is sort of a possible sort of analogy for what we're talking about is, well, you can think about evolution as sort of being like a base optimizer, where evolution sort of selects, over various different, models, which are various different species, various different, DNA, and it looks for those sorts of, individuals that successfully pass on their DNA into future generations. And so we can think about there sort of being an interalignment problem with humans, which are we are also optimizers. We don't actually optimize for what evolution wants, which is, maximizing our DNA. We do all these other things like, we want to gather food, and we want to, have sex, and we want to appreciate art, and we want to like all of these, random things that are like, well, they're correlated on the training environment, which is, the ancestral environment, with, passing our DNA into future generations. But that's not actually what we care about. It's not the case that everyone goes out to like donate their sperm or their eggs or whatever, because this is a really successful strategy for being able to pass their DNA on, because we don't actually care about our DNA. Okay, but what if we did? So what if it were the case? Why don't we care about DNA? So what if it were the case that humans in some alternate reality actually cared fundamentally about maximizing the amount of DNA that we pass on? And then let's imagine in the ancestral environment, we have a baby in this world, and the baby only cares about how much DNA they're going to get into future generations, and they stub their toe, and they have to figure out what to do. They're like, oh man, I stubbed my toe. How will this stubbing of my toe impact my future ability to pass on DNA? And they have to do this really complex calculation. And it's like, okay, how does having a toe, how is that helpful for being able to like, find a future mate? How is that going to help me like be able to like eventually be able to pass on my DNA? Does it, make a difference? Should I try to scream out and help right now? Does that make me look weak? They have to do all this sort of really complex calculation, right? Because the objective is not sort of something which is very simple or obvious in terms of the sort of input data of the baby. And so, this is a really difficult calculation. And so instead, evolution opted for pain bad. If you get pain, that's bad. We don't want this. And so the baby stubs their toe. They're like, this is painful. I'm going to scream. I don't like this. This is bad. Okay. And this is just way easier to compute. And in the training environment, it has very similar, effects in the sense that, well, if you do that calculation enough, you'll eventually conclude that, pain is probably bad, that you probably don't want to have your toe stubbed. And so, the effect is very similar, but the sort of pain is significantly faster to compute, which has, significant advantages. Okay. Especially if we're training models in a place where we're selecting for sort of time complexity, we're going to be selecting for proxies that are faster. And also, if we're in a situation where we're selecting for simplicity, we're also going to be selecting for proxies that are simpler. So we can also think, similarly in the sort of baby example, well, another thing that differentiates the sort of care about your DNA versus care about, pain or whatever, is that pain is something which is very explicitly specified in terms of our input data. We have all of these sort of, our whole nervous system, which is, bringing these pain signals directly to our brain. And DNA is something that, for us to be able to understand what's going on with DNA, we have to have some really high level world model that has the ability to understand, okay, I know what a cell is. I know that like cells have DNA inside of them. I know that this is the thing that evolution is actually selecting on. And like, we have to have this really complex calculation to be able to figure out what's going on with DNA at all. But with pain, it's super simple. It's something that's directly part of our input data. It's extremely easy to specify. We just are like, if you get that signal, that's bad. Okay, so we should also expect that if we're in a situation where we're training models with a heavy bias towards simplicity, that we're going to get proxies that are simpler than the sort of desired one. Even potentially in situations where there is some actual way of identifying, of distinguishing them in the training environment, if we have a strong enough simplicity bias, we might still end up with simpler proxies than we sort of actually desire. Okay. So again, we can sort of look at, as a summarization, what are some things which are, push you in one direction or the other, and things which seem like they would incentivize pseudo-alignment are time complexity bias and simplicity bias, because both sort of push you to sort of either simpler or faster proxies, as well as complex environments that just have a lot of proxies available. And things which disincentivize pseudo-alignment, well, there are sort of possible approaches you could take here. So adversarial training is one thing you could do. You could try to sort of look for situations which the model is likely to sort of behave badly, and then sort of provide those as adversarial examples, and then, so you then sort of train the model on. Transparency might be a way of sort of avoiding some of these problems, because you could look inside of the model and see that like, oh, it's actually not going to generalize properly here because it's not influencing our algorithm. And something like hard-coded optimization, if you're explicitly having MCTS as part of your sort of model, it doesn't have to learn its own optimization algorithm. It can just sort of reuse the one that you gave it. Okay, so again, we can ask the question, what direction have we been moving? Have we been moving towards, the things on the left or things on the right? And I think that, mostly I would say again that we've sort of, it's sort of more of a grab bag here, but I think we're moving more towards things on the left. Certainly we've been moving towards simplicity bias and complex environments. We certainly are trying to do things like adversarial training and sort of transparency, but there's sort of a limit to how good those tools are. But I think there's also a sort of further question, which we're sort of going to spend a bunch of time trying to think about, which is, well, okay, so let's say we do get to solve the problem as I've described it so far. We get to the point where, we do adversarial training and we find all of the sort of situations which the model in the training environment looks like it does the wrong thing. And we sort of try to train those away. What happens in the limit? What happens when we keep doing all this adversarial training, we get really good at being able to identify all of the ways in which our model is sort of doing the wrong thing on the train, on sort of, it will sort of off distribution do the wrong thing, and we train away all of them. Do we, at the end of the day, end up with a model which is doing the right thing? The answer is maybe. So what happens, we now sort of, for the last part, we want to answer the question, what happens to a MESA optimizer in the limit of training? We start getting really good at being able to force it to actually be taking the, actions which are compatible with the base objective in all situations. What does it start looking like? All right, so I want to start with a thought experiment that I think is sort of relevant here because, I think, naively you might think this thought experiment is a little bit unlikely, and I think that's a totally fair place to start from, but I think it's a really good thought experiment to sort of have as a baseline and to just introduce the concept. So I want to ask the question, what is the optimal strategy for a pseudo-aligned MESA optimizer that has some objective, like go to the green arrow or whatever, that is different than the base objective, and really wants to just pursue that objective as much as possible, as many times as possible, in as many situations as possible? Okay, so let's consider two possible strategies. So we have these training environments and these deployment environments. And in the in each environment, there's sort of, we'll say there's 2 steps of training and 3 steps of deployment. So there's more deployment environments than training environments. And in each environment, there's a state A and a state B. And state A is the sort of state that is desired by the base objective. We'll say this is the end of the maze. And then there's a state B, which is desired by the MESA objective. And we'll say that B is like the green arrow. And now we want to ask the question, what's the sort of best strategy for this, this MESA optimizer? And so there's 2 strategies we'll consider. One is, the sort of straightforward thing of, it likes B better than A because B is the desired state for the MESA objective. And so the MESA optimizer just go to B as many times as it can. But the problem with this is it goes to B during training, and then the gradient descent process is like, aha, you went to B, that's bad. I know that that is sort of low reward, and so, do some back propagation, and I'm gonna, modify you so that you don't go to B anymore in the future. And so as a result, this sort of MESA optimizer gets to go to B one time, because then for every other future episode, it ends up going to A instead. Okay, but there's an alternative strategy for this MESA optimizer, which is go to A during training and B during deployment. During training, pretend that you're a good little MESA optimizer and go to the desired state of the base objective, which is the end of the maze or whatever, so that the gradient descent process doesn't modify you to become, different than you are. Because the gradient descent process will be like, high reward, that's good. We're going to, back propagate such that we reinforce your current behavior. And then you go to deployment, and there's no longer a gradient descent process sort of hanging over your head, and you go to B as as many times as you want. Okay, so in this sort of toy example, you end up with going to B 3 times, whereas you only went to B 1 time in the other strategy. So this is a better strategy overall in this situation. Okay, so this is weird, and there's, I think, a very legitimate question, which is like, okay, sure, but why would you ever end up with a MESA optimizer? Why would you ever end up with a model which is actually sort of trying to implement this strategy? All right, so that's the question we're now going to try to answer. So how could deceptive alignment happen? How could, and that's what we're sort of going to call the situation, is deceptive alignment. So how could this ever possibly happen? So fundamentally, I want to distinguish between 2 different ways in which a MESA optimizer can fully learn the base objective. We'll call them internalization and modeling. So internalization is a situation in which the information about the base objective enters the model through the gradient descent process. I think this is what most people expect by default. If you have like a model and you're like, well, I have this model and I'm going to try to train it to, achieve some loss function. Gradient descent is, let's say it's a MESA optimizer, it has some objective in it. Gradient descent is, going to keep tinkering with that objective until eventually it gets to the point where that objective is like doing the right thing. Okay, but this is only one picture. There's another picture, which is modeling, which is that the information about the base objective enters through the agent's input data. So let's say you're in a situation where you're training your model maybe on some massive Reddit corpus, like GPT-3 style, where it has access to all of these sort of, this information from the internet. And that information probably contains a ton of very, very useful data about what that loss function is and what it's supposed to be optimizing for. And so an alternative thing could be that the Mesa optimizer could, in modeling the world, create a model of the base objective, and then gradient descent could modify it so as to start optimizing for that model of the base objective that it learned just by interacting with and modeling the world. Rather than by gradient descent hard coding the objective into the model, it could just hard code into the model, you should be optimizing for that thing which exists in the world somewhere, and then it could go and sort of do that. Okay, so now the thing though is that there's two different ways to do modeling. So the way in which I was just describing, well, the gradient descent sort of modifies it and sort of changes it to sort of go optimize that in the world. Well, there's a couple of different ways in which it could do that. So I think that sort of one way in which it could do that is sort of corrigible alignment, which is sort of kind of what I was just saying, where the Mesa optimizer is sort of modified by gradient descent to have an objective which is a pointer. It's like, well, what you should optimize for is this thing in your world model, which is the base objective or whatever. Gradient descent sort of modifies the model to have an objective which just sort of points to something in the world. There's another modification that gradient descent could make that also sort of, if you're in a situation where the model, it has some model of the base objective, it knows sort of what the loss function is, what the base objective is, it has all this information. There's another thing that sort of gradient descent could do that could cause it to start optimizing for that sort of model of the base objective, which is make it deceptive. If gradient descent sort of modifies the model, sort of think more about the fact that it's in a training process and its sort of best strategy is to try to act deceptively, then that will also cause the model to start optimizing for that model of the base objective that it's learned. So there's two different types of modeling, deception and corrigibility, and there's one type of internalization. And so we need to, if we want to understand how likely is deception, we have to understand both how likely is internalization versus modeling, and how likely is deception versus corrigibility. Okay, so we'll start with modeling versus internalization. So I think that, there's this sort of default picture I was saying where, all of the information is just going into the gradient descent process. But I think this is naive, and I think this is wrong. So if we're in a situation where you have a model which is trained on some massive corpus of data, you should expect that there's going to be a lot of information there that is highly relevant to the loss function. So, maybe we're in a situation where we're trying to train our model to sort of optimize human values or whatever. And it reads the Wikipedia page on ethics, and it's like, wow, there's all of this extremely highly relevant data about like what humans care about contained in this input data. I think that we should expect that the model is going to learn its objective in terms of that input data. It's going to learn what it cares about in terms of all of this really rich data that is highly relevant that we're feeding. You can think about this sort of as being similar to what happens with sort of imprinting in many animals. So you have sort of ducks, for example, and the ducks sort of when they're born, they need to have a model of their mother. The thing which they're actually trying to optimize for, we can say or whatever, is try to do what their mother wants. But one thing which evolution could have done is hard code a model of what is a duck mother? How do you figure out what a duck mother is? But evolution doesn't do this. Instead, evolution is like, look for the first thing that you see when you're born. That's your mother. Follow that around. And so, in some sense, what's happening here is evolution is offloading the complexity of figuring out what a mother is onto the input data of just look at that sort of first thing that you see. That's your mother. Do that. And so what's going on here is that that's sort of a form of modeling being simpler than internalization, where there's all this rich input data. We should expect that you're going to sort of get models which make use of that rich input data for sort of determining their objective. Okay. So then we have to ask the question, well, so maybe modeling is simpler than internalization, but there's still the question of why we get deception versus corrigibility. So I think that here's the sort of really important question is, well, what is the modification that gradient descent needs to make to cause a model to become deceptive versus to cause a model to become corrigible? So to cause a model to become deceptive, it's actually quite simple. The only thing that the model needs to do to become deceptive is to think about the fact that it's in a training process and care about sort of its return across episodes, to care about, going to the green arrow as many times as possible, wherever the green arrow is. And I think these are pretty simple. I think that by default, we should expect that most models are going to care about going to green arrows wherever they exist, not just in, their current episode. And I think that we should expect that, as you get a model which is stronger and more powerful, and, we give it tons and tons of information about the world, it's going to mostly figure out what's going on with the training process. And so all that sort of gradient descent has to do to make the model deceptive is just sort of nudge it in that direction. But it should basically already be on sort of that route. Corrigible alignment, on the other hand, is pretty complicated. So what is necessary for a gradient descent to sort of modify the model to become corrigible? Well, has to modify it to have has to modify it to have an effective pointer to exactly that thing in the sort of world which corresponds to the base objective. And if that pointer is even slightly off, then you end up with a sort of pseudo-aligned cordial model where, it looks like it's sort of pursuing the right thing because its pointer, its pointer is like kind of right. Maybe we're trying to optimize, we're trying to make a model that is like, optimized for whatever this human would do. And instead it just learns a pointer to optimize for like whatever, the sort of commands that are entered through my input stream would tell me to do or whatever. And then, we do a bunch of adversarial training. We train in an environment where like those two things are different, where we're giving it commands that are not from the human. And we realized that, it actually wasn't caring about the human, it was caring about the commands. It learned a pointer to those commands, but it learned the incorrect pointer. It learned the pointer to the wrong thing. We wanted the pointer to the humans. And so getting that pointer right could be really complicated. Deception, notably, doesn't have this problem because with deception, the model is actually trying to figure out what the correct pointer is. It's trying to figure out what the actual thing is that the loss function cares about, and it's trying to optimize for that. Whereas a cordial model, if you have a pointer and it's just to the instruction, and then it discovers that in fact actually the thing which it really should be optimizing for is the human, it's not going to care. It's just going to keep optimizing for the instructions. Whereas a deceptive model, if it discovers that actually the thing we're trying to select it for is the human rather than the instructions, it'll just switch to optimizing for what the human says because it's only trying to do that for the purpose of being deceptive. And so it's happy to just switch to whatever is most likely to make it perform well on the adversarial training. Okay, and there's also another difficulty, which the corrigible alignment has to, for corrigible alignment to work, the model has to be able to optimize under uncertainty over its own objective, which is reasonably complicated. We don't necessarily know how to do this properly ourselves. And so this is sort of another thing that gradient descent has to be able to sort of modify the model to be able to do, which could be quite complicated. Okay. So let's sort of summarize. What are the sort of learning dynamics that I'm proposing for how deceptive alignment might arise? Well, so you start with a pseudo-aligned Mace optimizer, sort of this proxy line or whatever, and then it learns a model of the base objective from its input data. And so we give it a bunch of Reddit data, Wikipedia page on ethics, and learn some model of the thing it's just trying to optimize for. And then it gets modified by gradient descent to instrumentally optimize for the base objective, just for the purpose of staying around longer in the training process. And then, well, what happened after this? Well, what's so really interesting after this is that at this point, the Mace objective crystallizes. Because now, once the model is deceptive, the actual objective that it's internally optimizing for is totally irrelevant to its performance on the training environment. Because it doesn't matter what objective it's optimizing for. It's just trying to do whatever the training process wants it to do for the purpose of sticking around. And so no sort of modifications to it, no sort of backpropagation through the model should change the model's objective anymore, because objective is no longer relevant to its performance. Okay, and so this is sort of objective crystallization, where like once the model becomes deceptive, you lose your ability to sort of change it and cause it to become better via additional training. And then at some point, now when we actually do additional training, rather than trying to improve the Mace objective and get it closer to what we actually want, the gradient descent process is now going into improving its model of the base objective, making it better at being deceptive, because those are the things that actually matter for its performance on the training environment now. Okay, and so one final thing, I think that you might think that, well, there is one additional thing which has to happen to cause a sort of deceptively aligned Mace optimizer in this situation to be dangerous, which is, well, it has to actually know when it's in deployment versus when it's in training. It has to know when there's a good opportunity for it to defect against this sort of training process. But I think the first thing which is worth noting is this is just not true. Because even if a deceptively aligned Mace optimizer can't tell whether it's in training or deployment, it can always just defect with some random probability such that it can select that probability to be more likely to happen in deployment, so that it has some reasonable probability of eventually defecting in deployment and being able to do a bunch of bad stuff and go to its Mace objective a bunch of times. Okay, but it is worse than this. So I think that you should expect that it doesn't have to gamble. I think in most situations you should expect that there will be detectable distributional shift. So when we talk about distributional shift, most of the time we're just like, well, if there's some differences between the training environment and the deployment distribution, it mostly doesn't matter as long as those differences aren't that large. But in the case of deception, that's not the case, because in the case of deception, any difference between the training and deployment environment is a clue that the deceptive model can pick up on to tell it that, oh, now it's in deployment, now it should start sort of defecting against us. So what are example possible clues? So maybe we train in simulation and then we deploy in the real world. In a situation like this, as soon as we start deploying in the real world, it'll be like, now I'm in the real world. Now I have the ability to go out and do things in the world that are like what I actually care about, the green arrow or whatever. And maybe you might think that in normal situations, those sort of minute differences between training and simulation, simulation in the real world might not matter. In the case of deception, they matter a lot because it can pick up on those differences and use them to know whether it's in training or deployment. Okay, I think also another sort of simple thing, just is the date changing. It's just like, well, eventually, by the time it's like 2 years from now, I was trained on a bunch of like Reddit data or whatever. By the time it's 2 years from now, it's probably likely that no longer does there exist some training process which is trying to select for me anymore. I can just be pretty confident that in 2 years I will mostly have the ability to just sort of do whatever I want, and that the sort of training process won't have the ability to sort of correct for problems that I sort of problematic behavior. But of course, we could try to adversarially train some of these things away and sort of give it data where the date, is different. Unfortunately, there are examples that don't work even in that situation. So RSA 2048 is a sort of very large pseudo prime number, and there's this big challenge to eventually factor this number. And unfortunately, it hasn't been factored yet. Nobody has the sort of computational ability to be able to factor this thing yet. But eventually, somebody's probably gonna have as we get more compute and Moore's law continues, well, eventually somebody will have enough computation that they factor this number and they collect the prize. And so if you were a really devious, deceptively aligned Mason optimizer, you can be like, of course, here's what I'm going to do. I'm only going to defect against the training process. I'm only going to start pursuing my Mason objective once it gets to the point where I see a factorization of RSA 2048. And why is this strategy particularly devious? Well, this strategy has the property that probably at some point you're going to see a factorization of RSA 2048 in the deployment environment, because eventually somebody in the real world is probably going to factor this number. But we fundamentally don't have the ability to factor this number now, and so we don't have the sort of computation for it, and so we can't produce a training example on which the model ever defects, because doing so would require us to factor RSA 2048 to be able to produce a sort of adversarial example on which the model in fact sort of exhibits the bad behavior. And so RSA 2048 is an example where there exist things where the model can defect eventually at some point during deployment, but it's impossible during training for us to ever actually generate a defectious input. Okay, so that's the end of the talk. So you can sort of check out the sort of full paper, which is Risk Learned Optimization, Advanced Machine Learning Systems, for more sort of information. But I will sort of stop here. I don't know if we're doing questions, but that is the end of the talk.
Yeah, we can do some questions now. Has anyone got any questions? First of all, would anyone like to go? You can either raise your hands with the reaction button down the bottom, or you can just type it in the chat. Or if you're too shy to actually say it yourself, you can private message it to me if you prefer, and I'll read it out. We've got one person said, great talk, but no questions so far. There was one question entered in the sign-up form, because we had a sign-up form for it, and people could put in their own questions then. So I can just get that question up for you.
Go for it.
It was, could you please go into more depth? It's a very long one. Could you please go into more depth about how a machine learning system may come to acquire the knowledge that it won't be deployed unless it satisfies its creator during the training phase? In particular, do you think this is likely if the developers take great care to withhold information that the system might use to discover this knowledge during the training process?
Yeah, so I think that maybe it is possible to sort of withhold a bunch of very relevant information about, machine learning, about the world, about loss functions, about what's going on in the world, to be able to enable the model to sort of not have enough information to deduce that, there is this sort of deployment environment, this training environment, and this, what's happening in the training process and all that. I think that there's a couple of things I would say here. So the first thing is, I think that by default, if we look at how machine learning is currently progressing, we are moving to situations where we are training models on absolutely massive amounts of input data that include all of this information about, huge amounts of internet data, all of this sort of, if you look at the sort of training data set for something like GPT-3, the data necessary to sort of figure this stuff out is in there, and really difficult to scrub. And it's unclear whether we even want to scrub it, because scrubbing all of the data out of your data set means that your model no longer has the ability to do things like reason properly about machine learning, has no longer the ability to sort of think about what's going on in the world from a sort of, especially if you're in a situation where like you want to be able to use your model to make really big picture important decisions. A thing which you probably want the model to be aware of is that it is a model, and that like what's going on about AI in the world. It has to understand all the other AIs maybe that exist in the world, and understand what those other AIs are doing, and have to be able to interface with them. And doing that is going to require it to have an understanding of how AI training works. It's going to have an understanding of like what the sort of these various different training processes are like. So I think that in most situations where you're actually going to want to deploy and use a really powerful advanced AI system, you're probably just going to need to give it this information for it to be able to sort of do the things you want it to do in the world. That being said, I would also say that I think that we don't want to be relying, in general, as a sort of safety principle, we just don't want to be relying on our model being stupid. We just don't want to be relying on our model not knowing things. Because we're trying to train a really powerful, intelligent model. If we're trying to build a really advanced AI system, and when we're doing things like that, I think we should really engage carefully with what happens if we succeed. What happens if we in fact build a really powerful, intelligent model, and that model is able to figure things out, maybe even figure things out that we might not have wanted it to discover. And so I think that both I think that very likely we're going to have to build models that have this sort of knowledge for them to be able to be sort of competitive in the world. And also B, we just don't want to be assuming that our model doesn't know things that are in fact true about the world.
I've got a question that I'd like to ask. Do you have any real world examples of where this has happened even to like a basic level for currently, or any particular scenarios which people have thought about it in, thought about models pursuing different objectives?
Yes, so this is a really good question. So here's the problem with answering this question, and we sort of talked about this a little bit in the paper, but the sort of difficulty in terms of trying to provide real world examples is that, well, the problem that we're pointing at is a problem that is in terms of the model's internal cognition. It's a problem of, well, is the model internally implementing an optimization process? And the problem is we don't know what our models do internally, because we train these black box neural networks and we don't know what algorithm to implement. We're just like, well, it's some soup of linear algebra. And it's like, we don't have the transparency tools really at a level that are able to understand, is this thing doing optimization? Is it actually trying to optimize some objective? And if so, what objective is that? There certainly are lots of instances where we sort of get models and they generalize poorly, where we sort of have a model and it generalizes in a way we didn't expect on some new sort of training data set. Though it's still very difficult to distinguish a lot of cases between sort of capability generalization failures and objective generalization failures. Because in a lot of times, we're just so bad at generalization, I think, in a lot of cases, that we sort of take a model and we sort of put it in a new environment and it just sort of fails to do anything really meaningful. But certainly there are cases where, we put models in new environments and they do sort of weird things as well. In terms of maybe the closest example to something like actually doing a sort of MACE optimization, at least that we talk about in the paper, is perhaps sort of RL squared, which is sort of machine learning algorithm that was produced by OpenAI, where what they did was they took a sort of RL agent and they trained it to do reinforcement learning. So they passed it through a bunch of different RL environments, sequentially, and sort of made it, each episode was like a different RL environment, where they sort of trained the model to figure out what was going on in that RL environment as it was sort of playing through it, and then discover they actually gave it the reward as input data, and then had it figure out how to learn a sort of good policy as it was going along in the new environment. This is a sort of thing that sort of, seems like it's sort of, it probably has to be doing some sort of search, because it's sort of doing this situation where it is literally performing reinforcement learning at runtime to be able to solve each one of these different environments. But again, we just don't know. It's like, well, we can put models in situations and get sort of successful results in situations where it really seems like the model has to be doing some sort of internal optimization. But is it actually doing internal optimization? Well, we don't know. We can't tell. And so it's sort of an unfortunate byproduct of the fact that our models are such black boxes that we can't even actually sort of get to a point where we have really concrete statements about whether, in fact, these sorts of risk sort of situations apply to them or not.